Hello and welcome to presentation session 3 in the second week of SeptembRSE. This afternoon we've got 3 presentations, 2 talks, both on a similar theme to do with medical imaging from Tom and Michael. We'll have a short break at about 3 o'clock, a comfort break of 5 minutes, and then the last presentation in this session will be a walkthrough of the software package SunPy. As a reminder, these sessions are being recorded and also we are bound by the code of conduct from the Society of Research Software Engineering. If you have questions during the talk for the speakers, you can submit them in the Slido website for each talk. So Christopher has posted in the chat the link to the Slido for Tom's talk, and I think what I'll do now is hand it over to Tom Dorick. So please take it away.
Hi, let me just get the video on. Thanks, Chris. I will share my screen and then we can get started. Okay, can everyone see this screen? Yep.
It's a bit cropped on the right hand side. It looks like we've only got the left half.
Yes, let me just stop and stop. Start screen. Better. Is that any better?
Yeah, that's good.
Right. Yeah, so hi everyone. My name's Tom. I work at UCL, and I'm going to be talking about generating synthetic data for use in medical imaging applications. Yeah, so I've fortunate enough to be awarded one of the recent round of RSE fellowships from the SRC, which I just started last month. I've been at UCL since 2013, working on a variety of different medical imaging and medical device applications, most recently for augmented reality on liver surgery, which sort of links into a bit about what I'm talking about here. Anyway, so the topic of my fellowship is improving research translation in image-guided surgery, and I'll just talk a little bit about what image-guided surgery is first. So image-guided surgery is essentially any surgical procedure where the clinical team is using something other than their own sort of hands and eyes to guide the procedure. So there's an example here, which is a neurosurgery application where they're using a tracked pointer to overlay on CT data. And another common example is any kind of keyhole surgery where there's a camera inside the body along with some surgical tools. Now, the advantage of IGS is that it's generally less invasive for the patient, so they don't have to stay in hospital for as long and there's fewer complications, but it can be more difficult for the surgical team to go ahead with it. Now, pretty much everyone I know who works in IGS is looking at machine learning in some way or another. So registration, segmentation, stereo reconstruction, etc. But because medical data is quite different from real world data that other imaging algorithms are trained on, a lot of models that might perform well on sort of standard computer vision tasks don't translate very well to medical data. Now, if you're working on machine learning, there's a few different ways you can typically go about making your model better. You can add more data to your model. You could look at a different network architecture, or you can do some hyperparameter tuning. But if you're working in medical imaging, it's very, very difficult to get more data. So most people are looking at the moment are looking at novel architectures or some kind of parameter tuning, which kind of, I think this and this kind of limits the range of it limits how people have to look at the problems. They always look at it from a sort of a network architecture point of view rather than a data point of view. And there are many reasons why you can't get hold of a lot of data for medical imaging. So there's patient confidentiality. They often don't want to share. Even if data is collected, it's not necessarily going to be shared widely outside the institution. So, for example, I have data I've collected at UCL that has been collected at UCL that we couldn't share with anyone else. Also, if you're looking at an application that needs kidney data and someone's only shared liver data or heart data, then again, you've got a bit of a problem. These data sets are also often very small compared to something like ImageNet, which has millions of images. Your medical data set could be as few as 10 or so different examples. I talked about restriction on data sharing linked to confidentiality. Another problem is that getting accurate ground truth data or accurately labeled data is quite difficult. Either you need to have a trained clinician come in and look at your data and annotate it for stuff like segmentation, or even just bounding boxes. But then some things like stereo reconstruction, there's no way you can collect stereo data from inside someone's body. It's not really practical. So one of the things I started looking at is, can we use synthetic data to train some models in medical imaging? And so there have been some applications of synthetic data in the wider computer vision community with some data sets such as Virtual Kitty and Scene Flow. And there's an example here from Virtual Kitty of some synthetic self-driving car data where they're labeling and getting some depth maps. Advantages of this are that you can generally get more complex and more accurate labels. You can get potentially more data. But also you're not fully capturing the true case. So there's this issue with the domain gap, which is where you might perform well on synthetic data, but there's still something missing when you go to real data. I think with medical data, because you don't have that training data, it's kind of the trade-off isn't quite as important, because it's sometimes it's either train on nothing or train on something that's at least approximating the real life application. And you can always, it's quite common to train on synthetic data and then post-train on some real data if you have it. Now, about a year or so ago, Unity, which is primarily a games development engine, started releasing some packages, which I think they're currently in alpha or beta still, for doing large-scale simulation of computer vision data in Unity, which has worked out quite well for me. And basically, it allows you to set up a Unity scene. You can script it as you normally would, and then you can randomize certain parameters within the scene. Say, this example on the right here is randomizing object position, object rotation, texturing, background, stuff like that. And then it's generating the labels at the bottom. So this is doing instant segmentation of this data, and that's all done. All the labeling is done automatically. You can combine this with any existing Unity functionality, so animation, render pipelines, particle effects, and it's also very, very fast, because it's just rendering as fast as your computer can render frames. So I can easily get thousands of frames of data per minute. And if you really want to go high, you can split across multiple nodes, so you can run multiple instances of Unity on different computers, and that gives you more data. So this is it. You can implement new randomizations, new labelers, just using Unity scripting, which is on C#. It's relatively straightforward. I've been doing a little bit of this since I got started last month. And so what am I actually doing? So I'm trying to say, can simulate data be useful for model training in medical applications? And the first problem domain I was looking at is liver segmentation. And this is more, it's not necessarily because this is an area where we need a new model, but it's an area where I'm already familiar with the problem domain, and we actually have some good real data to be able to compare models to. So this is sort of a brief example of some different simulations I've been doing, just segmenting out the liver. So yeah, I've been looking at setting up a scene in Unity, like in the bottom left here, which with a liver model and then some slightly odd background texturing. And then I've been able to vary model position, rotation, textures, model normals, objects occluding the scene, and then look at like different lighting and even things like lens distortion and camera focus, which is, you will always get between different data sets, different camera parameters, so things like that can have an effect. And I've simulated, tens of thousands of frames of this data. This is sort of a bit of a collage on the right-hand side here of some simulations, some of which are a bit abstract compared to the real life scenario, but these are some slightly more realistic video simulations, just showing the sweep over the liver. And again, this is just a sort of a small amount of them, but it still gives you the general idea of what's going on. Now, this is all simulated data as well. So there are other ways that people are looking at simulating medical data, because it's a common problem, right? And so people have taken image to image transfer and video to video transfer from sort of the wider computer vision community, where you sort of take you have a content image, which is this one, so it's one on the top left, and you have a style image, which would be some real surgical data, and then you combine them, and this generates your synthetic medical data here. Now, I think this can be quite complementary to what I'm looking at, which is simulating the whole thing, because I think with this kind of image to image transfer, you end up getting more realistic texturing out, but you also need to have some data in the first place to train on. So it's kind of the same issue as I was talking about before, is that if you didn't have some real data that already exists to train your model on to get the textures out, then you can't necessarily do it. Something I'm going to look at is sort of combining these two approaches to get some sort of a wider range of data. And also you can, this approach, you still need to have the 3D scene in the first place, so that there's 3D scenes at the top of the images. And we can use Unity to generate a lot more scenes a lot more quickly than you could do manually. So it's still quite early in sort of what I'm going to be doing this for a month or so. I've got a lot of stuff to add to my simulation, so soft body physics to model some more complex organ interactions, particle effects for fluids, water, blood, etc. I've generated a lot of data, and I think in general, I'm getting some, I'd say, acceptable results. The actual model training with synthetic data. What I need to do, I do need to do a more sort of formal comparison of what the segmentation quality is, using different combinations of simulation and real data. I also need to expand to different organs, different conditions, and then one sort of big area I'm going to be working on, maybe not a bit later, is to look at what I'm calling multimodal simulation, where you can get the same scene and you can simulate your visual data. You can simulate perhaps CT or ultrasound as well, and this will require quite a bit more work. But you can take the 3D scenes you've generated in Unity, I can convert them to a finite element model, and then if I have a solver for ultrasound data and a solver for CT data, I can then run sort of large scale simulations on all these different meshes I've made, which will probably end up using some kind of HPC or GPU solution as well. Final thing, in order to make these scenes, you need to have the actual models themselves. So there's a few ways of doing this. One is 3D scanning. We have a 3D scanner I can use. You can buy some models from the asset stores, and also I think some things can be procedurally, programmatically generated. So you could generate new models and new textures sort of on the fly, just by twiddling some parameters. Brings me to the end, so I'll stop sharing and take any questions if there are any.
So we've already got a couple of questions in Slido. I think here comes the screen. So if you've got any more, please click on the link that is in the chat, and we'll pose them to Tom. We'll start with the first one. For medical imaging software development, what are the challenges over and above normal RSE that are required for certification, regulation, etc.?
Yes, I think I do. I do bits of work within sort of a regulated medical environments, so not all the time, but little bits. And generally, there are I think it's IEC 60601 or something like that, which sort of specifies what procedures you have to go through to write medical device software in the UK, and there's a similar one for the EU and a similar one for the States. I think one of the bigger things that it talks about is having sort of an auditable, traceable trail of the decisions you've made and what choices you've made as you're designing your software. So it's not, it doesn't specify, you can use whatever language you want, you can use whatever way of testing you want to do, but you have to be able to sort of document what decisions you made, why you decided to make something, why you decided to do something, and then what you did to do it. I think one of the problems that this brings up is that often people will start a project and then maybe 1 or 2 years down the line might think, oh, this might be a good medical device spin out, but then they've often then got to go back and do everything from scratch because they didn't they didn't document their thought process at the time. So it's a bit of a balance between, obviously not everyone needs to do this, but then if you're, so you have to try and think about what stage you're at and whether you think you're going to need this in the future.
Cool. So there's a question about overfitting in deep learning. Well, that's what I'm paraphrasing it as. The actual
I mean,
question.
this is always a very big risk, right? Yes, I mean, there are, I guess, two aspects of this. One of them is that, so like this liver example I was giving, is, I said it's not that useful an example because we actually have quite a good model trained on several thousand real cases that have been annotated by a clinician, but there literally could be some cases where you might only have 5 or 10 examples. So it's even allowing for the fact that you could overtrain on your synthetic data. If you've only got synthetic data, then it's a better start than nothing. And then you can at least sort of bootstrap your process and then post-train. And also it helps, I think, develop, UCL is quite well attached to different hospitals. So we have a lot of clinical access. If you're working somewhere where you don't have clinical access, or you don't have clinical access for the case that you want, then you can either say, okay, well, I could never train a model because it might overfit a bit, or I can at least start and have a look at what some of the things. And because the other side of it is that I think you could in principle do some very realistic simulations in Unity, which I'm hoping to get towards as I go through my fellowship. So yeah, I think you've got to balance off having some data is better than no data, and also try and make it as realistic as possible to try and avoid these artifacts.
What advice would you give to a research software engineer who has been asked by a researcher to start working in this area?
So I don't know whether that's medical devices generally or synthetic data. I guess it might be medical devices or medical applications. I think it's important to understand sort of the practical clinical challenges that you might encounter when you go to try and deploy something. So, for example, we had worked on a project with using machine learning to manage applications. That might be okay. So you'd have to look at, I guess you want to find out what data they already have, what they're hoping to achieve with it. But I mean, I don't have any particular. I'm not a machine learning person myself. If you follow, so I can't give too much advice from the machine learning side of it. I work with some good machine learning people who might have some better answers, but I don't necessarily have any particular advice to someone other than, yes, explore what data they do have, explore what access you have to clinical staff who can label the data for you if you've got real data. So if you've got medical data that's unlabeled, that's also not that useful.
It's unfortunate because I think the next two questions are also machine learning questions.
Yeah.
So how do you ensure you have a good diversity in the synthetic data?
Yeah, that's, again, it's not something I've particularly, well, I've thought about it in the sense that I'm aware that different diseases change the look of the liver. Yes, if you've got a particularly heavy drinker, the liver might be a different color. Where I think these brief answer is that because it is so easy to vary the parameters in a simulation. So, for example, the color of the liver can change as you get older, or you have particular diseases, and you can easily within Unity create a randomizer to tweak the texture of your liver to adjust the color. So things like that, and then adjust shapes and sizes. I don't actually know off the top of my head what the differences are in livers across races and gender, but it's important to try and look at those things, I suppose.
And again, on technical aspects of ML, how do you write good tests for machine learning output? What guarantees or confidence levels can you give regarding the performance of the software?
Again, can't give a great answer to this question because I'm not at the moment sort of a particular machine learning expert, but I know enough to keep me going. But again, I'll have to pass on that one.
Okay. Parameter tuning. So for what parameters can you tune for machine learning and image guided surgery?
Well, it's more just the general parameters of your model. It's not like there's anything particular for IGS. So if you're doing, if you could people fiddle with network dropout and optimization rates and learning rates and stuff like that. So there's nothing particularly unique to IGS that I'm aware of.
I think this one is similar to the question a couple back.
Yeah, so again, yes, I am worried about it, but if it's better than having no data at all, I'll go with it, and then I'll see where we get to.
Cool. I think that has exhausted the supplier questions. So if there are no latecomers, we will thank Tom for the talk. Thank you very much.
And thank you everyone for listening.
And we'll move on to Michael, if you want to share your screen.
Unmute myself.
Yep, we can hear you.
Share screen too. And can we see that?
Yep, perfect.
Brilliant. Okay, so yeah, I'll get started. So I'd like to introduce my talk on OSIPI, which I've been calling the open source initiative for perfusion imaging. Turns out it's now officially the Open Science Initiative for Perfusion Imaging, so we're going to come back to that name change later. But OSIPI is a project I've been involved in for about the last 18 months or so. And as the name suggests, it's a global collaboration of researchers that have realized that the science and research they do is to some extent being limited by the software tools we've been using, and consequently wanted to do something about this. Now, because it's a global collaboration and because I wasn't involved in OSIPI from its inception, I thought it would be good to hear about how the project is structured from those that were there from the start, and maybe try and take advantage of the online format. So I've done something a bit different for this. The main content of my talk has kindly been provided by the current project chair, Laura Bell, followed by two of the task force leaders. So I'm hoping the videos they've sent me are going to work. So without further delay, I'm going to let Laura, who's the current chair, give an overview of the project as a whole. Please holler if you can't hear her.
My name is Laura Bell, and I'm going to be speaking about a community-led open science initiative for perfusion MRI post-processing. So a quick overview, magnetic resonance imaging, MRI, is a medical imaging modality that can capture both anatomical and functional information of the body's organs. Within MRI, a heavily researched field is that of perfusion. It's a technique that measures the amount of blood flow through various organs after post-processing these MR images. Perfusion MR, through decades of research, has been shown to be useful for various aspects of clinical care, from diagnosis, disease progression, and treatment response. However, the clinical adoption of perfusion MRI remains to be slow. In 2018, an International Society of Magnetic Resonance in Medicine, ISMRM, perfusion study group recognized reproducibility as the primary blocker. And so just to give a quick overview of this initiative, it actually started in 2015 by one of our researchers, Fernando Colamanti, and he led at our annual
Should we be hearing audio?
Perfusion MRI freeware. So a handful of people got up and presented about their open source perfusion software. In 2016, it continued. But then in 2017, nothing happened at our annual conference, and in 2018, again, nothing happened. So at the end of our conference in 2018, we kind of decided to regroup and think this through. We decided to send out an initial survey to the ISMRM perfusion group. We had over 100 responses, which was a pretty good response rate considering a perfusion group was about 600 people. And then from these responses, we identified 7 people to join together as a founding board to go through the survey results and really figure out how we were going to sustain ourselves, our mission and our aims. So following the next year in 2019 at our annual conference, we held a member initiative symposium where we presented ideas for this initiative. And then right afterwards, we had a face-to-face where we had about 50 people who were interested in this come. And this is where our task forces were created. And I will talk about that in a few slides. And last year, by 2020, we were endorsed by ISMRM, our parent society, and then officially integrated into the Perfusion Study Group. OSIPI's mission is to create open access resources for perfusion imaging research in order to eliminate the practice of duplicate development, improve the reproducibility of perfusion imaging research, and speed up the translation into tools for discovery science, drug development, and clinical practice. We have identified 6 aims to help support this mission, and each one of these aims are supported by our task forces. So as I mentioned, we have 6 aims. Each aim has at least 2 task forces to help support this. And the 2 task forces come because perfusion imaging can broadly be divided into 2 different methods. So each perfusion method is its own individual task force. So we have the first one, a software inventory. So here's a curated list of the open source and actual commercial software packages already available to use. 2 is a toolbox. So this is where we have open source functions, scripts, and pipelines for analysis. 3, data. So you need data to be able to test these software packages. 4, reporting, which is also a very important part of post-processing. How are you going to report the image acquisition parameters as well as assumptions made during the analysis? 5 is a platform for exchange. This is for users and developers. And then lastly, benchmarking. So we can actually go ahead and use the data from the AIM 3, and then we can benchmark the post-processing pipelines through AIM 1 and AIM 2. A current status of who we are today, we are a management team of 4 people. We rotate out every year. We have 10 task forces. Each task force is led by 2 people, a lead and a co-lead. And then within task forces, we have task force members. So we're about 50 people altogether. Work is carried out at a 2-year delivery cycle, just because we're so large. This is going from May 2020 to 2022. And our deliverables and milestones are all outlined and updated every 3 months when we meet. In 2022, we are currently expecting 11 to 12 manuscripts focused on the various aspects of these aims. And ideally, we have tried to build OSIPI to be a sustainable, evolving initiative supported by the community. And I just want to point out all the task force leads as well, and thank all the members who participate in these leads. Thank you.
Okay, so following on from that, 2 of the task force leads that on task force that I'm kind of working or related to the work on are going to present their area now. So starting with Ina, who's working on one of the reporting task force.
Hello, my name is Ina Kompan and I'm the lead of the Dynamic Contrast Enhanced DCE and Dynamic Susceptibility Contrast DSC MRI Lexicon Task Force of OSIPI. We're an international group of 15 people who committed themselves to writing a contrast-based perfusion MRI lexicon. So why are we doing this? Many software platforms exist to analyze perfusion data. However, the comparison of the analysis results across different software platforms and publications is difficult due to, on one hand, a large user variability in the reporting, due to no clear consensus on how to document applied analysis processes, and finally, due to no standardized nomenclature of quantities and processes. However, a key element in ensuring perfusion reproducibility is the standardization of nomenclature, such as naming parameters and reporting of processing pipelines, both of which are currently lacking. As a part of OSIPI, we aim to develop a perfusion analysis lexicon which provides a standardized nomenclature for perfusion parameters and typical analysis pipelines. Additionally, we provide a framework for reporting DCE and DSC analysis pipelines as pseudocode based on the lexicon. Overall, our aim is to standardize reporting in order to improve the reproducibility of perfusion analysis. Since the scope of such a lexicon is inherently very large, we didn't find it feasible to come up with a complete lexicon all at once. Instead, our approach is to provide the structure of such a lexicon filled with initial basic content. The design is chosen such that the content can be easily extended and is meant to be a dynamically growing inventory which can be updated by the Perfusion community. To incorporate feedback from the community, regular feedback cycles are planned. Additionally, I would like to mention that the lexicon and reporting framework are merely of a descriptive nature and do not provide recommendations on how to perform the analysis. However, we do want to make sure that the content of the lexicon is aligned with initiatives providing such recommendations, and that the relevant items to describe recommended processes are present in the lexicon. Have I piqued your interest? If yes, then please have a look at our publicly available document for details of our work, such as the structure of the lexicon and the usage of the reporting framework. Of course, we are always happy to receive feedback on our work, so please feel free to leave comments directly in the document. At the moment, the items of the lexicon are arranged into tables in a text document. This makes it difficult for the user to actually apply the lexicon. Therefore, as one of the next steps, we aim to improve the user experience, for example, via a searchable web interface. In close collaboration with the OSIPI Code Library Task Force, we aim to, on one hand, help to shape the structure of the code repository, and on the other hand, use the lexicon to report the workflows of the collected code snippets. Ultimately, one of our main applications is to amend the DICOM standard for the purpose of communicating DC and DSC MRI parametric maps in order to improve data sharing in a standardized way. Hello, my name is Ina Kompa.
Hello, I'm Michael Thrippleton from the University of Edinburgh, and I'm one of the co-leads of the OSIPI Code Library Task Force, along with Petra van Hout of the Netherlands Cancer Institute. Good software is essential in perfusion imaging, and that's demonstrated by this figure, which shows the same piece of head and neck data processed using different software packages. And as you can see, the results are very different depending on which package we use. In OSIPI, we're starting from the point of view that we want to be doing open science. So we want to do science that is reproducible, reliable, and transparent. And that means, at a very minimum, we need code that is open source and that is well documented and well commented. And going beyond that, we'd ideally like to be using code which is maintained in the long term, so that people can take the code we've written and use it and develop it further. And also we'd like to be using code that is community driven. So it means we're processing data in a way that reflects the scientific consensus and not just the approach taken by me or by my lab, for example. To address these challenges, we formed a task force back in early 2020, which presently stands at around 20 members. And we cover a range of domain expertise, so we're all medical imagers with expertise in different parts of the body or in different diseases. And we have some research software engineering expertise as well. We're all volunteers and the project is unfunded. So we take a consensual approach to most of what we do. So whether that's deciding our aims, deciding the scope of the project, setting out the roadmap, as well as actually implementing that roadmap, it's generally quite consensus-based. And because we're spread out across the world, we make a lot of use of collaboration tools such as Slack, GitHub, Google Docs, and so on. Our task force has three aims. The first is to collect existing snippets of open source code for perfusion imaging so that we can make these accessible to the perfusion community. The second is to validate the code so that we have a collection of code that is trusted for both scientific users and software developers to use. So we'll have this big collection of code which contains contributions from labs across the world in which do all sorts of different things in terms of functionality. And our third aim is to try and bring these all together into a single OSIPI Perfusion code library with a single API. And the hope is that this will become the standard Perfusion imaging library, because it will be community-led, it will be sustainable in the long term, and it will be designed to be modular and extensible. So if somebody develops a new technique, then it will be easy to incorporate that in the software library. And underpinning all three of these aims is the idea of software skills transfer, because most of us in the task force are scientists, and although we have some coding experience, we have limited skills when it comes to things like version control and unit testing and so on. I'd like to give you a brief overview of the progress we've made. In our first strand of work, which is code collection, we've set up a GitHub repository. So if you'd like to see that, please visit the URL at the bottom of the slide. Now, most of us in the Perfusion community code in MATLAB, that's probably the most common language, or Python, and we've made the decision to collect only Python code for the moment, because obviously it's an open source language and it's freely available, and there are lots of useful scientific libraries written in Python. So far we've collected 29 distinct code contributions coming from 9 different authors, and most, I guess, of those authors are from members of the task force, but also we have contributions from the wider Perfusion community. Our second aim is to validate, in a scientific sense, the code that we're collecting. And to do that, we've chosen to use a unit testing approach, and in particular the Python PyTest package. Now, to do scientific testing, you need test data, and we've obtained that from members of OSIPI and also from other open science initiatives that make data publicly available. And one of the advantages of the unit testing approach is that we can automate this in our GitHub repository. So if you're a scientist looking for code and you decide that you want to use some code in our repository, you can click through and see whether or not it's passed the tests that we've set up. And our final aim is to develop a new code library for Perfusion Imaging. And we've already made the decision to develop this library in Python. And where it's feasible, we'll be basing this on code that we've already collected and validated within our code repository. The library is going to be designed and structured around the OSIPI Perfusion lexicon. And that means that when we want to specify a processing pipeline or describe a processing pipeline, we can do so clearly and accurately. So at the moment we're finalizing the library design. It's become apparent that to make this a reality, we'll need both sustained scientific input, but also input from people with research software engineering skills. So at the moment we're seeking funding opportunities to pay for that. So that's where we are at the moment. If you'd like to know more about the work, then feel free to contact me or Petra.
Okay, so next, the challenges team had sent me a contribution. Unfortunately, due to time, we're going to skip over that, but the video is available offline if people would like to see that.
My name.
So just to finish, I thought I'd like to add a few thoughts of my own on the project and why I thought it would be a good topic for SeptembRSE. So firstly, I'm a fellow of the Software Sustainability Institute, and their motto being better software, better research. And although OSIPI encompasses more than just software, obviously that idea is really at the heart of the project. But then on that theme and going back to this issue of the name change, so when I linked back to the main OSIPI website on submitting this abstract, I was embarrassed to discover that we were actually the Open Science Initiative for Perfusion Imaging, and I'd been all the time calling us the Open Source Initiative. But it turns out that I wasn't going mad, and the leadership team had recently agreed the name change to better reflect the broader open science questions the project was now addressing. And what I find interesting about this is I think that it shows that it isn't just that better software itself makes for better research, but that by thinking about the processes and structures we need in place to create better software across the research community, that kind of expands to improve how we think and implement other key areas that contribute to reproducibility in science. And then thirdly, I think OSIPI is an interesting project in that many aspects of it fall within the scope of RSEing, but really it was conceived and very few of the contributors are RSEs or would identify as such. So as Michael said in his section, we're mainly scientists who code, but that have together recognized that a more formal RSE approach would benefit our area in many ways. So to give an example of that, I've been in meetings with scientists and clinicians that had never previously heard of a unit test. And we're there having long discussions on the differences between unit and integration testing and what an appropriate testing framework for our code might look like. So I think you've got this really receptive group of researchers wanting to know more about the RSE world. And therefore anything we can do to facilitate those discussions within the wider RSE community can only be a good thing. And finally, I thought this would be an interesting topic because although perfusion imaging might seem that something it's quite a niche area or very specific, the reasons that OSIPI were established are much more general than just perfusion MRI. So summarizing the contributions the task force leads gave, I think the key characteristics of this area that apply more generally are one, that we produce numbers that have meaning in the real world, and therefore there's a real obligation to try and get them right. But then those numbers are produced by complicated acquisition and or analysis pipelines. So there's a lot of things we need to get right to try and validate those numbers. But in doing so, we have no universally used or standardized analysis software, structures for reporting those analyses, or testing frameworks. So if that sounds like it might also apply to your research area, and or you're involved in a similar project to OSIPI, or perhaps you may even be inspired to start something similar in your area, we'd love to hear from you and get that feedback. So that just leaves time to thank the people that have contributed directly to the talk and also to helping submit the abstract, and open the floor for any questions.
Thank you, Michael, and your horde of contributors. We do have questions. Here they come. So we'll start at the top. How many members of this large collaboration are directly involved in writing software? What are the challenges of managing software across a large group?
Great. Well, I'm just going to try and put my video on so you can actually see me. It's not video. Oh, sorry, it's saying I can't start my video. Sorry, can I see that slide?
I'm not sure how to get Chris. So the challenges of the large managing software across a large group.
Yeah, so I mean, I think that's it is a challenge in this area. To an extent, I think in the early part of the project, we were kind of having to make that process up as we went along. So it was kind of led by the task force lead. So, and initially I was involved in two task force. One was the one that Michael presented about collecting code. And then there was a second task force that was kind of dedicated to what has now become that end goal of the code collection task force, the writing a kind of combined library. And I think sort of the way those task forces themselves have changed over time, and effectively one's become defunct and become a goal of the other, tells you something about the challenge of trying to, manage this sort of project. So I think to the extent that we make it works by lots of communication within each of the task force, trying to be very open that on the overall aims we'd like to achieve, trying to assign people that have time to the right task within those, but also being clear that within the scope of this project, you know, you can't necessarily set hard deadlines on things or expect that people can, you know, can definitely contribute a certain amount of time. Then the challenge of maintaining software across such a large group. At the moment, we're kind of at the collect everything that's out there stage. The next stage, we're looking more at the kind of harmonization stage. So I think that's where this challenge is going to come in. And we've had, these are discussions I've been involved in a lot myself. And I think our view is at some level, you've just got to kind of tell people what you're going to do and then try and get feedback on that. And then once we've established exactly what our specifications are going to be, then try and assign those tasks back out. But I guess we'll see in a year's time.
So also on the subject of the software development, what processes are you following that would make the code easier to maintain? I guess if you're not doing that, what do you aspire to do to make the code easier to maintain?
Yeah, so I think what we're trying to do in this is that, you know, a lot of research code and the code that's probably been submitted thus far is the classic, you know, starts as a few lines and then expands as more functionality needs to get added and gets tinkered with by different PhD students and postdocs and God knows who. And then you end up with this kind of sprawling mess in some cases, I think it's fair to say. I think what we've tried to do in this is take a step backwards and say, well, okay, we're going to collect that, but then we're going to try and do this more formally, like, you know, you would specify a piece of software from the outset and say, these are the functions we need to have across our community. Let's document those first. Let's put a proper design in place for what we think that, you know, what the library is going to need to look like to solve those problems. And then at that point, start adding in the code. So that's kind of, you know, that's how I guess software engineering is meant to happen. It isn't often how things happen directly when researchers write software. So I guess we're hoping that by following that kind of process and by having the specifications well documented and the design well documented, that in the long run, that will make it easier for the community as a whole to maintain.
So you touched on the documentation of the specification. I guess this question about documentation is probably more wider in scope, like, you know, once the library is written or is in the process of being written, and end user documentation, SDKs, etc. Do people write documentation? How do you encourage them to write more?
That's a very good question. So, well, I think people have their own experience of how much people write documentation. I think it's fair to say most of the code we've had contributed hasn't got fantastic standalone documentation. I mean, personally speaking, I've been working on, separate to OSIPI, our kind of own internal code base for Perfusion Imaging. And one of the things I've tried to do for that and spent a lot of time on is writing some very thorough documentation for everything our internal code does. So this person does. And I'm hoping that will provide a template that we can use in the Harmonized library. I think to encourage them more, and then possibly seeing sort of some of the next questions, I think this goes back to that the final point I raised about there being, you know, a receptive audience. I think, you know, the whole OSIPI came about because the community wanted to do things better. So I think in many ways the stumbling block now has been people knowing what they need to do. But I think once you've got, you know, like once we put the testing framework in place, or even simpler, once we, you know, a lot of people have never really used GitHub, at least not as something that they actively contribute to themselves. So, you know, initially people were emailing us code, and then once we put some very clear instructions on, you know, how you submit like a pull request and how you create forks and how you can push up your own code, people started doing that. And then similarly with the testing, once we kind of explained how you write some testing for your code and how you can do that, then that's been farmed out to various people that wrote their own code in the first place that are now writing testing for it. So similarly with the documentation, hopefully that, you know, once we explain what it is we need, people understand the benefit of it, then hopefully that will come.
Cool. That sort of answers the next question about the RSE type processes like GitHub, etc. But how do you communicate these to the other members of the team, the non-RSEs?
Yeah,
how do you sell RSE?
I mean, this is coming from my personal opinion, but one of the things I think resonates in this audience is that, you know, a lot of the people will be people with a physics background and may have come into this through MR physics. And these are people that really understand things like QA and QC in terms of how the scanner works. So, you know, you get that you've got like this £1 million scanner or whatever, and then it needs regular testing. And that there's a difference between, say, your kind of weekly tests that you might run that give you a quick overview that everything's working, versus, say, the more detailed test that an engineer might come and do if a fault comes in. And then, you know, they're familiar with the idea of, say, like having formalized and standardized phantoms that you put in a scanner that you come out and they, you know, you're at the image level and how the scanners work and you kind of have testing there. I think it's more that in the past that had never really, the way kind of coding was taught in research to them, those same sort of concepts, you know, didn't come into the software process. But actually, I think they're really receptive to the idea that, well, actually this post-processing, you know, once you've gone past medical imaging just being something about getting a pretty picture to actually we need to get some quantitative and measurable numbers that mean something out of these images, then all that same kind of QC and QA has to go over your software. And then, you know, then it's just a case of translating kind of concepts they get into RSE language.
Possibly a shorter answer for this question. How are the workflows described and run? Are standards like CWL used?
So I think so workflows in that meaning
image processing pipeline.
Pipelines, yeah. So no, and that comes into, I guess, the combination between what the lexicon task force is and what we're going to put in. And I think so. One of the, you know, the key selling points we hope for in terms of the library we come up with in the end, and to sort of persuade people away that, you know, if you did have your own code to start using this kind of community endorsed thing, is not just that it would be a more standardized library all round, but that it will have standards for describing the workflow put in place. But it isn't there yet, so by definition, no.
The next question I actually saw come in before it was mostly addressed in one of the videos. So we saw some screenshots of PyTest, and there was talk of the data, open data being available for that. So how will the code be validated? Do you have a publicly accessible validation test set? Could people use that to validate their own code?
Yeah, exactly. That came up. So in the this is kind of being addressed in various ways. So we're using small amounts of data to run the standard unit tests over the code submissions we have, but we're also collating a larger validation set that will be publicly accessible. Initially, that's being used in a challenges project. So the data will be accessible, the answers won't be initially, but then that will be made fully available so that in the future that can be validated against. And again, I think our plan is that we'll sort of have small amounts of data used to do things like standard unit and integration testing on the code library, but then we'll use perhaps a larger variety of code that we can provide demonstrations of how you run the analysis and the expected answers you get on that. As part of the, you know, kind of a demonstration, part of the documentation of the project.
Right, and we've got less than a minute to go and one question. It was interesting that the work plan targeted a number of manuscripts published each year. How much software is expected to be produced?
Yeah, good question. And you can tell it's still researchers at heart that are specifying the workflows. So that's kind of up to us in our part of the task force. So what on the kind of harmonized code library, that's the one bit that's intending to generate entirely new software. And how much what we would like is to have a harmonized library that does everything that the contributors so far, the kind of analysis pipelines that they run. So it will be, I would say, the most comprehensive software package for our area out there when it's produced. We don't have a hard deadline for creating that, but part of that is going to come on to, we're looking at getting some dedicated funding for this, which would hugely accelerate the process. So to an extent, we know exactly what we want to do. It's having the time and resources to be able to do that.
Well, good luck for all of that. Thank you very much for your contribution. If we can put a clapping emoji in the Zoom chat for Michael. And then what we'll do now is take a quick comfort break for 5 minutes. We'll come back afterwards, and Shen, who was also in this morning's session on Python, will come back to give us a walkthrough of the SunPy package. See you in 5 minutes. Welcome back, and we're now about to start the last presentation in this session. Hopefully Shen is back at, yes, I see he's back at his computer, he's got his camera on, and if you want to go ahead and start sharing your slides, if slides are what you're going to do.
Thank you. Let's see. Oh, I cannot find my web browser. Where is it? Okay. Let's see what this. So I have downloaded here the content of the folder uploaded to the web. As you can see, there is a Jupyter notebook here. And there is a blank file. There's a walkthrough file and a blank file. And you can start with the blank file first. Yeah. So here in SeptembRSE, where I work, we are doing a project on analyzing the data from the sun, more particularly the emission from the sun, and especially the when the sun has most activities and it emits the highest emission signals, and we can catch it. And in this walkthrough, I'm going to show you how to use the SunPy package to analyze the files available online. So I have prepared this notebook for you. And okay, it just take a few seconds to open it, right? But now that we have to install several libraries, as I type here, particularly we have SunPy, zip, and DRMS. So you can use your command prompt or terminal, or you can insert a new code cell and then just right here. Okay, and there's a bit so you can see. So we are using the Python 3 kernel, and we can just run this because my system has this library already installed.
Are you there, Chen? I think we've lost the connection. We'll just hang on a minute or so and see if it comes back. There are a lot of upsides to remote conference, but one of the downsides is the peril of the network connectivity. I'm just waiting a few more minutes to see if this is a temporary thing. Yeah, Shen can reconnect. Otherwise, we. Oh. So the news is he's back. We're just doing the behind the scenes Zoom magic to get the presentation back up again. And so Chan, if you can hear us, you should be able to start sharing your screen again. So we can just see in the chat that there's a Wi-Fi signal problem at Chan's end, and he's going to continue the walkthrough from the desktop PC. So we're just waiting for that. There we go. So we've got the notebook. We can't hear any audio, but that may be a limitation of the hardware at that end.
Hello?
Hello, we can hear audio. Awesome, we're back again. So yeah, please continue. I spoke too soon. We still can't.
Hello, can you hear me?
Yes, I can hear you now.
Oh, I'm terribly sorry.
That's okay. These things happen.
Okay, so we have to switch to my desktop and the video signal is not available. So you cannot see me now, but you can see my screen.
Yeah, we can. We can see the notebook.
Okay. So as before, we use this template, the blank file, and install the libraries needed. So let me introduce a bit more about this SunPy project. The Python programming language has found its way to physics community quite some time. And before, the physics community used the IDL language. And as you can see in the chart here, many older researchers still use IDL to some extent. But the new trend for graduate students and undergrads, they are using Python more often. And yes, SunPy is one of the new libraries that tries to adopt the Python language. It was built on an older code base in IDL called SolarSoft. And by now, the SunPy has reached its 3.0 version, which is quite a major achievement. And the version has been worked well on Python 3 since 2019. So in this short walkthrough, we can obtain the data from the web. There are plenty of data of different types there, and this here's what I reused one example from the gallery of SunPy. We read the AIA format, and which is a quite interesting type of data. It's quite an established source, and there is a sample map sample built in this SunPy, and we call it the AIA 193 image. Yeah, so you can just execute the first block of code. And as it's built in, then the execution is quite fast. Okay, I think it may take some time on your system, but then you have it. So this variable was stored in this image is stored in the variable AIA map, and then we can use matplotlib to see the map of the sun surface. I think the next block of code you can see. We can identify the bright spots on the image and with a darker background. You see, interestingly, the sun is not a uniform sphere of uniform brightness, but there are dark spots and bright regions. Actually, the scientist has to convert the scale of brightness, but for now we just use this one. And also on this image you can see the date and time where this data has been captured, and this the degrees, the degrees of longitude and latitude of the sun. And next we can extract this data to find interesting patterns, particularly the local peaks, where in this image is the brightest. Is it this one or this one? Okay, let's see. To make it easier, we install the scikit image package, which help us to identify the local maxima for this data set. So this next block of code will help us to get that data. Okay. So after plotting it in 3D, we can see where the peaks are. There are two major peaks, this one and this one, which are marked by these red dots here. But you also see that the coordinates are different from that of the previous image, previous map. That is because while the standard plot is made on a grid, the latter one we see here is on the standard plot function, plot 3D plot, which is not built in the SunPy. So it's a bit different, and it's from here it's a bit difficult to find out which point is which in this plot. So we just print out the coordinates, this one, and you see not 2 but in fact 6 points appears as a peak. Yeah, we can find out by executing the next block of code. Yeah, and yeah, it has a new function to convert the coordinates of this index in this grid to the location on the map. And as you can see, the 6 points are clearly shown on the map by now. Okay, and I also provide you a link to an example gallery, and in this gallery they show us how to make further improvement to the image to enhance the edge of this and detect where the coronal loops are. So you can follow this link, and Okay, and then you can see the example, and you can apply the same techniques to this image to find out, to sharpen the image and find out interesting patterns. Aside from getting the data from a sample, we can analyze existing file store on the system. Here in the subdirectory SECI, I have prepared file for you, and this is a compressed file, but SunPy can manage with it. We can run this one, and we can plot. First, we can find out what the data are. In one typical file, there are two types of data, which are the image and the file header. For the image, which is a NumPy, simply a NumPy matrix, we can plot it. And we can find the statistical information. And for the header, we can find out the relevant information, which is stored as a dictionary. And we can plot it as before. And we receive this one. In this image, actually the sun is only here, and it is covered by an opaque screen, which limits the brightness, and we can only saw the corona part outside of the sun. This one is a FITS file, which is the FTS extension, and we can systematically download it from the web by using the FIDO interface. To use the FIDO interface, we have to install two additional libraries, which are zip and DRMS. You can install by this bang command like here. Sorry. And it will run on your system, and then download and install the relevant packages. Okay. So after installing, you can import the data. You can search the data from the FIDO. Here we search from the 6th to the 7th of July 2017. And we can see that we have some results here. Yeah, the results are prepared in a table, and you can see the start date and the end date, start time and end time of the observation, as well as the instrument used and the wavelength and the file size. Okay, there are many records, and we want to limit the data to only relevant one, and we just search for the relevant info in the info and file ID fields of this record in the SECI output. And we can execute this to limit the result to this one, but still too many data to be downloaded. So we limited to the first 5 items here. Okay, and we shorted it into 5 items, and we create a file. We name it with this format, and we store it in the current directory by using the FIDO fetch method. You see some progress bars for the 5 items. So actually there are 5 items, but this will kind of collect to one unique file. It will appear on the same directory with yours, which is the file starting with 2017 and ending with N4C2A. Okay, so that comes to the end of this walkthrough, and hopefully you retrieve this file, and this is actually overwritten in the same directory with yours. Yes, it's at the end of this walkthrough, and thank you for following me.
Thank you very much for presenting that, Shen. That was very clear, the notebook. I don't have cause to do much Sun image processing myself, but if I did, I now know exactly where to start. We've only got one question so far to you, which is, it's great to see that the software is working well on Windows. Is it portable to other operating systems, e.g. Linux and Mac? Are there any challenges to deploying Python on Windows?
Thank you. Actually, this package is better suited for Linux and Mac. Yeah, and initially I tested on Linux and Mac. On Windows, a long time ago, I remember that there is some problems with when I first installed SunPy. Yeah. But I didn't record it. Yeah, there's some problem with installing. Maybe it related to the permission for installing in my office. But for Linux and Mac, it runs flawlessly, and I was able to install both in my dual boot system in the office and on my Mac as well. Yeah, so
good.
Yeah, so now it's for Windows, but actually it's better to run on Linux and Mac.
So we've got less than a minute remaining before 3:30. One final question: how many developers work on SunPy, and how is the development managed?
Yeah, as for the SunPy report on last year, there was 100 people working on SunPy. Yeah, and now the number fluctuates over 100, and the development they have PEP themselves. That's an enhancement proposal. And yeah, and first they propose some new features to be added to SunPy, and then it will be revised by their group, and if any promising features will be implemented by the group. And you can maybe I'll provide a link to that to answer your question.
If you could, that would be great. Thank you. And that brings this session to a close, and SeptembRSE for today to a close. The next thing that's happening, other than being able to wander around the GatherTown conference venue, the virtual conference venue in virtual night, the next session that's happening is tomorrow morning at 10 UK time, and we will have a workshop then. I'd like to thank Tom and Michael and Shen for presenting this session. If we can get a round of applause in the chat, and we'll see you tomorrow.